Hello everyone, this lesson is about current and potential difference in circuits. This is the first lesson in the electric circuits unit for A-level physics. The intentions of this lesson are for you to be able to apply an understanding of current, potential difference and resistance in series and parallel circuits. This will involve you knowing some definitions and some equations, and then being able to apply those equations to the circuits. Starter activity: recall as many electricity equations as you can from GCSE. Make a list. Are there any component symbols that you can't identify from those shown here? Pause the video for a moment and do that. Current is defined as the rate of flow of charge. It's given the symbol I. You may have met some models before of electric circuits. In these models, what is being used to represent the current, the flow of charge? So we know that inside a metal wire we have got some metal ions which are vibrating around fixed points. They form what's called a lattice structure, which is a very regular repeating three-dimensional structure. And then there's some loosely held electrons, which we might refer to as free electrons. These electrons can and do move around through the metal. In the top diagram, when there's no potential difference applied, these electrons will move randomly in all directions, and the net effect is zero transfer of charge. In the bottom diagram, if there's a potential difference applied, you can see the plus and minus symbols there. Electrons will drift towards the positive terminal of the battery or the power supply that's connected, so long as there is a complete circuit connected. And the effect of that drift of the electrons will be an electric current flowing through the metal. Current is defined as charge divided by time. That could be written as I equals delta Q divided by delta T. Q is a symbol for charge, which is measured in coulombs, and time is measured in seconds. And we can then define the amp as the unit of current as being 1 coulomb per second of charge flow. So current is a rate of charge flow. Remember, when we talk about a rate, we divide by time. A worked example for you to try: a current of 2.0 milliamps flows through a component for 2 minutes. Calculate the charge that has flowed. Pause the video, write your working down, and then you can check in a moment. So we'd be rearranging the equation to get charge equals current times time, and then we've put our values in. We have to remember that the current is 2 milliamps, so that's 2.0 times 10 to the minus 3. That's then multiplied by the time in seconds. We're given that's 2 minutes, so we have to multiply that by 60, so it's 120 seconds. So it's 2 times 10 to the minus 3 times 120 equals 0.24 coulombs. So we have to remember to use the correct symbol for charge. That's the coulomb given with a capital C here. The equation for potential difference is given here. Potential difference equals work done divided by charge, or V equals W divided by Q. And from this we can define the volt. The unit of work done is the joule, and the unit of charge is the coulomb, and therefore the unit of the volt, 1 volt, equals 1 joule per coulomb. So the volt is a measure of the energy transferred to the circuit per unit of coulomb that is transferred. Here's a question, a worked example for you to try. A light bulb transfers 20 joules of heat and light for every 2 coulomb of charge that passes through it. Calculate the potential difference across the lamp. So we're going to use this equation, V equals W over Q. So it's 20 joules divided by 2 coulombs equals 10 volts. check you're working. Hopefully that's fairly straightforward. We know that to make a circuit work, we have to connect some components up to a power supply or a battery. And it's the power supply or the battery that supplies the energy that can be transferred to the circuit. We can refer to the electromotive force or EMF of a power supply. The EMF is the energy available per coulomb of charge. So it's the total energy a cell or other power source supplies to each coulomb of charge. In series, we know that energy cannot be created or destroyed. So in series, the total EMF is equal to the sum of the potential drops across each component, V1 plus V2 plus V3. In parallel, we know each component has the same potential difference across it. So the EMF equals V1, which equals V2, which equals V3. You will have met the equation for resistance. Resistance equals potential difference divided by current. R equals V over I. The unit of resistance is the ohm, omega symbol, where we have voltage in volts and the current in amps. Worked example: the current through a 5 milliamp. The current through a resistor is 5 milliamps. When the potential difference across it is 0.4 volts, what is its resistance? So R equals V over I, which equals 0.4 divided by 5 times 10 to the minus 3, which equals 80 ohms. So just being careful that we're given the current in milliamps, so that's written as times 10 to the minus 3. We're now going to derive the rules for combining resistors in series and in parallel circuits. In a series circuit, what can you say about the current at each point in that circuit? For the same circuit, can you come up with an equation for V total and for R total, which will be the total circuit resistance? Alright, so we know the current at every point in a series circuit is going to be the same. So we can write I total equals I1, which equals I2, which equals I3. And the I1, I2 and I3 would just be 3 different points around the circuit where we are measuring the current. V total in a series circuit, we know that the total EMF of the cell is going to be shared across the components. So V total equals V1 plus V2 plus V3. And because V equals I times R, we also can write V total equals I R1 plus I R2 plus I R3. If we divide through by I, which is the same value through all the resistors and through the cell as well, we can get an expression for R total. So R total equals V over I, which equals R1 plus R2 plus R3. And that's, we've there derived our rule for combining resistors in series circuits. And perhaps we knew this already, that the total resistance was equal to the sum total of all the resistors in the circuit. R total equals R1 plus R2 plus R3. In parallel circuits, what can you say about the potential difference across each component? Can you come up with an equation for I total and for R total? So first thing to say is that we know that V total equals V1, which equals V2, which equals V3. The potential difference across each branch in the circuit is going to be equal to the EMF of the cell. Second thing we can write is that the total current is going to be equal to I1 plus I2 plus I3, where I1, I2 and I3 are the currents through each branch in the circuit. We can write that as I total equals V over R1 plus V over R2 plus V over R3. Just alternative way of writing I1, I2 and I3. Because V is the same value, on each side of the expression, we get I total over V equals 1 over R total, which equals 1 over R1 plus 1 over R2 plus 1 over R3. This is now an expression for calculating the resistance of the total resistance of resistors connected together in parallel circuits. So what you would do is take each resistor value and calculate 1 divided by that resistor value. You'd then do the same for the others and you'd add them together, and then you would have a value for 1 over R total, and then to find R total you would have to find the reciprocal of that, so 1 over that value. So we know that when we combine resistors together in parallel, the total resistance decreases. When we're talking about the total resistance, we're really thinking about the effect of those two resistors together in the circuit, and thinking that we could replace those two resistors with a single resistor which would have the same effect. Question: if you've got two 10 ohm resistors connected together in parallel as shown, show that the total resistance is 5 ohms. Pause the video and have a go at using this equation to show that this total resistance is 5 ohms. So we'd write that out as 1 over RT equals 1 over 10 plus 1 over 10, which we know is equal to 2 over 10, and then RT is a reciprocal of that, so that's equal to 10 over 2, which equals 5 ohms. When we have two resistors of the same value connected together in parallel, the resistance halves, and that's a handy rule to remember. So two 10 ohm resistors combined together in parallel gives us 5 ohms. Question for you to think about now and have a go at: calculate the current I1 in this circuit. There's two steps to this question. One, find the total circuit resistance, and then two, I'm going to use the relationship I equals V over R total to find the current. So looking at just the first step there, find the total circuit resistance. We've got two resistors in parallel, and they are connected to a third resistor in series. So you're going to have to find the resistance of this parallel combination and then add it to the resistor that's in series there. Have a go at doing that. Okay, so what we should find is that the two 40 ohm resistors give us a 20 ohm resistance combined together. And you can see the working there. 1 over 40 plus 1 over 40 equals 2 over 40. So our total equals 40 over 2, which equals 20 ohms. And that resistor is then, or that resistance is then in series with the 20 ohm resistor that's near the battery. And so add that to this resistor, and that will give us a total resistance of 40 ohms for this circuit. And then to find the current, we'd use V over R2, R total, which is 8 volts divided by 40 ohms, which equals 0.2 amps. So we found the current that flows through the cell and through this part of the circuit. Here's another question to try. Calculate the total circuit resistance. We've got these three resistors connected together in parallel. 100 ohms, 50 ohms and 25 ohms. And then 2, calculate the current through each resistor if I1 equals 0.2 amps. I1 is as shown here. Pause the video and have a go at this question. So for the first part, we're using 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. And we should find we get a value for 1 over RT of 0.07, and then for RT it's 1 divided by 0.07 equals 14 ohms. So we've found a value of these three resistors combined together, an effective resistance of 14 ohms, which is less than the values that each of these resistors has, which is, we know that's going to be the case when we connect resistors in parallel. Question 2, calculate the current through each resistor if I1 equals 0.2 amps. So we know that V total equals V1, which equals V2 equals V3. And we can calculate V total from I1 times the total resistance, which is 0.2 times 14, which is 2.8 volts. So we've calculated the EMF of the cell there, effectively 2.8 volts, but we know that's going to be the same across each resistor. So just to help us, we can mark on label the potential difference across each cell here, and then it becomes a case of using Ohm's law, or I equals V over R, to find the current through each resistor. And so through the 100 ohm resistor, we've got 2.8 volts on 100 ohms, so it's 2.8 divided by 100, 0.028 amps. Through the 50 ohm resistor, it's 2.8 divided by 50, which is 0.056 amps, should be an A there. And through the 25 ohm resistor, 2.8 divided by 25, which is 0.112 amps. So we've answered the question, we've calculated the current through each resistor. Note that the resistor with the highest value of resistance has the lowest current flowing through it. The resistor with the lower value has got the highest current flowing through it. We could check that this is correct by adding these three values together. We should find that we get 0.2 amps. So we're now going to look at potential difference in circuits. If we have a circuit drawn like this with 12 volts labelled, we can assume that the EMF of the cell is 12 volts. Assuming that the wires have negligible resistance, the connecting wires, we assume that there's no potential difference dropped across these wires, and therefore if we connected a voltmeter across this resistor here, we would expect it to read 12 volts. And that's because the potential difference across the resistor is equal to the EMF of the cell, which equals 12 volts. So note we use the term potential difference across resistor. So what does that really mean? So if we took 2 points in the circuit and measured something called potential, which is essentially the energy in the circuit at that point, energy per unit charge at that point, we'd see that to the left of the resistor, which is the positive side of the cell, we would have 12 volts, and to the right we would have 0 volts as shown here. And so what we're measuring is the difference between those 2 points, 12 volts and 0 volts, so the potential difference is 12 volts. If we look at how the potential difference varies across a wire, so ignoring the connecting leads and assuming they have negligible resistance, we're just going to look and see what happens to the reading on the voltmeter as we move this slider across. So it's like a connecting contact here that you can slide across from the left hand side to the right hand side. So our cell has an EMF of 12 volts. So what would the voltmeter read if the slider was all the way over to the right, for example, or if it was all the way over to the left? What would be the reading on the voltmeter in different places? So what we need to do is look at the potential at different points along the wire to see how that varies. So on the left hand side of the wire, we can identify a point where the potential would be 12 volts. And on the right hand side of the wire, we can identify a point where the potential would be 0 volts. So what would happen as we move this slider across from left to right is that the reading on the voltmeter would increase, and it would increase from 0 volts to 12 volts. Remember, what we're reading is a difference in potential. So if we just put this slider on the left hand side next to so there's no wire at all, it will read 12 volts, 0 volts, and then as we move it across to the right, it will gradually increase up to a maximum of 12 volts. With the slider in the midpoint, middle of the wire, halfway along the length, we'd expect the voltmeter to read 6 volts. So looking at how the potential along the wire varies with the length, it's the top graph here, you can see that the potential starts at 12 volts and drops down to 0 volts, and it's a linear relationship. So it's a gradual incremental decrease as you move along the wire. And if we then look at how the potential difference on the voltmeter would change, so the voltmeter reading, as you move the pointer or the slider across, you're gradually going to increase the potential difference, and again that's a linear relationship. So we could use this setup to give us a variable output from a power supply. So let's say we had a power supply with a maximum output of 12 volts. We could have a switch which we moved like the one we've got here from the position on the left, which would give us an output of 0 because there's 0 potential difference, along to different points where the output would steadily increase up to a maximum of 12 volts V out on the right. So it's a way of controlling a power supply to give you a variable output. We're now going to look at the potential difference across components. If you had two 100 ohm resistors connected together in series to a 12 volt power supply, what would you expect the volts, the V1 and V2 readings to be? So the potential differences across each of the resistors. So if you've looked at that and just said, well, it's going to be 6 volts across each resistor, then you would be absolutely right. But let's show that that is the case. So we could calculate the current from V total divided by R total. So that would be 12 divided by 200. So adding the two 100 ohm resistors together would give us a total current of 0.06 amps. We can then use V equals I times R to find V1 and V2. And it will be 0.06 amps times 100 ohms for V1, that's 6 volts, and it will be the same for V2, 6 volts. So we've actually shown there that what we thought would be the case is actually true. So if we've got equal resistors in series, then our 12 volts will split equally and we'll have 6 volts across each component. And if we look at the potential at different points, as we did before, we'd be able to say that there's a potential of 12 volts on the left, 6 volts in the middle, and 0 volts on the right, and that will give us a potential difference of 6 volts across each resistor. So let's have a think now about what will happen if R1 is changed. So taking our two 100 ohm resistors connected in series, let's take the left hand one and call it R1, and let's just think about what would happen if we now made that a 200 ohm resistor. What's going to happen to the potential difference across it? So we can do a similar thing to before. We can calculate the total resistance in the circuit, which is now 300 ohms. We can calculate the current in the circuit, which is 12 volts divided by 300, which is 0.04 amps. And we can then use V equals I times R to calculate the potential difference across each component. So V1 equals IR1, which is 0.04 times 200, which is 8 volts, and V2 equals IR2, which is 0.04 times 100 ohms, which is 4 volts. And so we can see there that we've still fulfilled the rule where the total, the sum of the potential drops has got to equal the EMF of the cell. So 8 plus 4 equals 12 volts. But we've now got a different split. It's no longer equal. And you can see that the component with the higher resistor has got the higher potential difference dropped across it. And in fact, it's in the same ratio as well. So the resistors are 200 to 100. They're in a 2 to 1 ratio. So the potential difference dropped across each resistor is in that same ratio, 2 to 1. The higher the resistance, the higher the potential difference dropped across it will be. So if you could review your learning this lesson, so apply understanding of current, potential difference and resistance in circuits. Can you define and use current, potential difference in equations? Define and calculate resistance. Determine current, potential difference and resistance for circuits in parallel and series. Well done if you've understood all of that, and thank you for watching the video. I look forward to talking to you on the next one.